So a brief intro about myself. I am Saurashish Chatterjee, a PhD scholar in IIT Kanpur in the Department of Electrical Engineering. And for this semester, I'll be holding the live problem solving session for this course titled 5G Wireless Standard Design. Okay, Dikshita, you have raised hand, so you have some specific questions. So you can just unmute yourself and ask.
नो सर बाय मिस्टेकली चली गया.
Okay, okay, oh, no issues. Okay, so I guess we can start. Let me enter the slideshow mode. So just one last confirmation. Currently I am in slideshow mode and you are able to see what I am writing on the content, right?
Sir,
In the red marking. Okay, okay, sure. Thanks. So the idea is somewhat like that. I'm supposed to discuss some questions which are structured in the similar manner to what you are going to see in your assignments and also in your final exam also. And the way I would like to proceed with, see, these are MCQ type questions. So if we are really solving in an efficient manner, this won't take much time at all. But the idea is to learn the concepts behind them, so that when we encounter similar questions, that is what is it presented in front of you, that is different from it, so you are able to solve it. Because you see, the questions can change, like questions can be tricky, it can be changed in a manner that it's difficult to answer. But if you know the underlying concept, that's going to be fundamental to uh, uh, like if you know a key concept, we can frame the questions in 10 or 15 different manners, but once you have good grasp on the fundamentals, you can answer all of them. So what I would like to proceed, like I will pick one questions, and I will discuss the key concept behind it. Mostly I will just repeat the important things from the lectures itself. So as you can see, that first question is about the minimum SNR required to achieve the capacity of 10 bps. So what is going to be the answer? So it's pretty much straightforward because we have this capacity SNR graph and all that. But more important to realize the relation between capacity and SNR. So can one of you please tell me what we really mean by capacity here? Like basically in the intuition, I'm not interested in the maths part, but what do you mean when you say capacity of a
I'm not
system?
seeing the question.
Okay, so is it for everyone, like are you able not able to see it at all?
Now we are getting.
Okay, so okay, just confirm me once. So I am entering in the slideshow mode now, so can you just confirm that, can you see these questions now?
Yeah, yeah, yeah.
You can see now, na?
Yes,
Okay,
sir.
okay, sure. So what do you mean by capacity? Can any of you please tell me that? Okay, let me just make the case a bit simpler for you. Let me talk about this. I think if you have gone through the lecture, you have seen this expression y is equal to x plus n. So now based on that you can say.
Here it is showing calculate its spectral efficiency. This is another question, I think.
Yeah, like okay, for y is equal to x plus n, basically what I mean, see, let's say y x is something that is being transmitted, and n is what is the noise. So when the noise is the
Sorry,
nature.
sorry, you are writing something. Actually, we are not able to see anything.
Okay, so I guess I need to now you can see it, right?
Yeah, yeah. Now
Yeah,
it's so.
Okay,
this is correct question.
okay, so most likely I cannot go into the slideshow mode, but I guess this is also okay, right? Like the screen is big enough for you to see the questions, right? Or
Yes, sir. This is fine.
okay. So let me just make it a bit more clear. That's okay. Okay, so yeah, so I just repeat the question then. Like what do you mean by capacity? And when I am asking capacity, I am asking in basis of this. Like for example, x is what you are transmitting, and n is noise, which is additive, and y is a Gaussian in nature. So we are calling it simple AWGN channel, and it's a single antenna system also, so all these are scalar only, y is equal to x plus n. So it's basically like you are transmitting x, and the receiver side you are receiving y, and that is some corrupted version of your transmitted symbol. So now based on that, what do you mean by capacity?
Number of bits transmitted through the channel.
uh, yeah, it's true to some extent. Like when I'm saying capacity of a channel, let me write it down. Capacity of channel, it basically indicates the maximum number of bits that can be transmitted with arbitrarily low probability of error. So yes, you are correct about that, like partially correct. It does indicate the number of bits you are able to transmit, that's true, but there is a catch in that. It is a maximum number of bits that can be transmitted with arbitrarily low probability of error. So what does it exactly mean when I say the low probability of error? That means when it says that arbitrarily low probability of error, that means you are almost always able to retrieve what is being transmitted. So that is what the capacity of channel denotes. That maximum number of bits you can transmit with arbitrarily low probability of error. So let's consider a hypothetical case. Like for example, you know, I guess already, that capacity unit is bps per hertz, that is bits per second that can be transmitted per unit bandwidth. So let me just write it down here. can one of you please mute yourself? There is a bit noise from your end, but I don't exactly see who it is.
I think it is Amshu Vinayak, I think.
Okay, okay. Anshu, can you please mute?
Okay.
Yep. Thanks, thanks. So it's bits per second per unit bandwidth. So when I say arbitrarily low probability of error, what I mean by that, let's consider hypothetically the capacity of channel is 2 bps per hertz. That means for per unit bandwidth per second I can transmit 2 bits of information with arbitrarily low probability of error. That says that in ideal situation, if I transmit at a rate less than or equal to 2 bits per second per unit bandwidth, in the receiver side I can always decode what is being transmitted. But the moment I am using the same channel to transmit, let's say 3 bits of information or 4 bits of information per second per unit bandwidth, the issue is the receiver will not be able to decode always what is being transmitted. So that's why the concept of capacity is crucial. It indicates the maximum capability of the channel to transmit information in an error free manner. And how exactly it is being related to SNR expression, that is given by Shannon capacity uh, theorem. So that your capacity R is given as log base 2 1 plus SNR. And how is this SNR thing related to here? So SNR is given by, let's say for this particular case, single antenna WGN channel is given by P is equal to sigma square. P is power of transmitted signal and sigma square is noise power. So with from this expression, what exactly we can say now? So this is what my capacity is, and this is what my SNR is. So what is the the relation between them? For example, if I ask you if the power of transmitted signal, let's say I reduce it, then what will happen to the capacity? Can one of you answer? I am reducing the power of transmitted signal. What will happen to the capacity of the channel?
Come again.
Yeah, I am saying that if you reduce the power of transmitted signal, what will happen to the capacity?
It also reduces,
It
sir.
will decrease.
It will decrease. And what will happen if I increase the noise power, like this sigma square term? Let's assume for some
It, de-
it will decrease again,
it
right?
also decreases.
Okay.
Yeah.
So at a in a high level, if I want to maximize the capacity, what is the requirement? Like if I want to increase the capacity of a channel, I need to increase the SNR, right? It happen both way,
Yes.
like you can either increase power of transmitted symbol or you can decrease the noise power, but actually the noise power in practical systems they are always kind of constant. So it's all about the power of transmitted signal. And not only that, actually, because this is a simplified expression where I consider the channel amplitude to be 1, actually what happens, you will observe y is actually is equal to hx plus n, and this h here denotes the channel gain. So your SNR is not p over sigma square, it's actually absolute value of h whole square p. So I have another parameter that I can play with. So it's a channel gain. So let's consider two scenario now. uh, if the user is close to base station and one user is far to base station, so what are the difference in value in this channel gain you think you will observe? Same user, I am considering one scenario when it's close to the base station and another scenario when it's far from the base station. What you will think happen to the
SNR,
channel gain?
SNR changes.
No, no, yeah, that is will happen, but what is happening at the most fundamental level? If I see this expression, scenario will change. That's true, absolutely true. No issue with that. I'm just want to start from the more simple explanation. Like if I look at y is equal to hx plus n, what we'll observe? Like
Noise will be more
The
for the
six
farthest
the
user.
signal power will be higher when you're closer.
uh, which signal power because transmitted signal power is constant in both the cases. Like what power with which I transmit, that is constant, that is p is constant. So which power is going, like which signal power is going to be more?
Channel gain will be more when it is closer, and it will decrease as we are moving towards
Yes,
edge.
absolutely. So transmitted power is constant in both the cases. If the received signal power, that is going to increase. So if I look at the SNR expression, this P remain constant because P is power of transmitted signal, that is constant. Sigma square, that is the noise power at the receiver end, that is also constant. The only variable here is going to be the absolute value of like absolute power of the channel gain. When you are close to the base station, your channel gain value is higher, so you are going to observe more SNR, and when you are far from the base station, your channel gain value is lower, so you are going to see low SNR. So is that another way of saying that when I am close to base station I am going to observe higher capacity, and when I am far from it we are going to observe lower capacity, right? So which case is more favorable to us, as we all use mobiles and all that? For example, I want to download a movie which is a pretty big size, like 2 GB or something. So which is, scenario is more favorable to us, being close to the base station or being far away from that?
Close to the base
Yeah,
station.
closer.
Close to the base
Close.
station. And how is that exactly going to help? Like if I am close to base station, what will change?
A number of bits transmitted.
Correct.
SNR.
So okay, SNR definitely changes, number of bits also changes, but if I say the file size is, let's say, 2 GB, so whether you are close to base station or you are far from base station, the amount of information you are going to download in your device, that remains same, right? So what benefit we get by being closer to the base station?
The rate of download might be higher.
Yes, so my per second received information is going to be much higher. For example, when I am close to base station, I might be getting capacity or spectral efficiency of 10 bps per hertz. So per second per unit bandwidth I am getting 10 bits. Whereas I am far from it, I might get 2 or 3 bits. So when I am far from the base station, I will take a lot more time, right? I guess that's what you mean.
Yes, yeah.
Sure. So this is a capacity versus SNR curve that is given in the lecture also. So I guess we are pretty much equipped to answer this question. I mean, this discussion was anyway not required. We can answer straightforward from the graph, but I am just trying to put in more intuitive manner. So what is exactly happening? So it's about the minimum SNR required to achieve the capacity of 10 bps per hertz. So which of the answer is going to be correct according to you?
Obviously, it should be more than 25.
Yeah, because it's not included. The point
Yeah.
the point is not included.
Yeah,
30 dB.
So it's either 28 or
either
30.
30 or 28,
I am not
or it
even
might be
sure.
35 also.
Yeah, I am not even sure about which one is the correct. But if I extrapolate this one, uh, it's stopping around somewhere around 8.5, right? I guess it's 30 most likely. But anyway, we can do the math from here. Okay, just let's do the math here. So it's given uh, R need to be 10 bps per hertz, right? So it's 10. So log base 2 1 plus SNR. So my SNR is supposed to be uh, 2 to the power 10, right? That is like roughly. It's not exact, but roughly. It's 1024. So if I try to translate into the logarithmic scale, so when they are asking the SNR in dB, what they are asking is what is the 10 log base 10 SNR value is. So it's 10 log base 10 1024. If I roughly approximate 1024 as 1000, so it's 10 to the power 3, right? So I can say 10,
It is around 30.
yeah. So it translate into roughly 10 to the power 3. That comes out to be 30 dB. So I guess 3 is the correct one here. And that is good time to introduce that first concept introduced by Professor Rohit in the course. I guess in the first or second lecture, the first key technology he talks about, that is adaptive modulation and coding. Right? I guess you went through that lectures to some extent. I just would like to briefly revise a part of it, why it is required and all that. So can you use this graph to uh, um explain why is the need for adaptive modulation and coding, like why it's exactly necessary? Okay, let me try to frame this question in a different manner. uh, Let me introduce a new slide. So next thing we are going to talk about is adaptive modulation and coding. So what does this term adaptive mean here? I mean, it is kind of self-explanatory that you can change it according to your need. Now I am more focused on like what do you mean by need. Before that I will write quite common modulation scheme. Let's say like 2 bpsk, uh, then qpsk, and let's say 16 qm. So first of all, data is not transmitted in a raw manner. I mean, it needs to be modulated and coded. Why it's needed, I'll come to that later. But can one of you tell me like what is the difference between these things like 2 bpsk or qpsk or 16 qm? What do I exactly mean by that? I'm sure many of are you like are familiar with these terms. So what do they really represent?
This first symbol will be different. Like BPSK will be having the least one.
Okay,
16
so
point will be different.
okay, so like if I look for 2 bpsk, so what are my two options?
So it will be
Zeros or ones.
one only one bit per symbol.
Yeah, so here you can transmit 1 bit per symbol, 1 bit per symbol, because you only have uh, two choices where you can choose from. So like now what is different about qpsk
It will
Two
be two
bits
bits.
per symbol.
and how you are able to transmit 2 bits per symbol?
because here we have four options:
Yeah, you have four
0,
options
0,
here.
0, 1, 1, 0, and 1, 1.
Correct. And what about like 16 QM?
Here we can transmit 4 bits per symbol.
Correct. Here you can transmit 4 bits per symbol. So let me pose a scenario when your SNR is like really bad. Like bad in the sense, if I go back to this curve here, the capacity versus SNR curve. Let's say I'm talking about this particular point. Uh, just a minute. This particular point corresponds to 0 dB and 1 bps per hertz. Do you think that choice of 16 QAM is going to be good if I am operating at that particular point here?
Yes.
No, it will be BPS only.
Okay, so why is that so? Because in 16 QAM I can transmit 4 bits per symbol, right?
Yeah.
So why
Yes.
BPSK?
Bits cannot be transferred if you use 2 BPSK, something like.
Yeah, true. Like what I'm asking, like for example, let's say I'm operating at this particular point, like my SNR is 0 dB only, so the plot says my capacity is 1 bps per hertz. So but I am willing to use the 16 QAM here because 16 QAM allow me to transmit 4 bits per symbol. So why not use 16 QAM here?
Because the channel capacity is only 1 bits and receiver can't decode more than 1 bits if we
Yes,
transmit to her.
But
correct, correct. So if I go from 2 bpsk to qpsk to 16 QAM, uh, just a moment. My screen got hang. Okay, fine. So here we are basically, you can say we are moving towards higher modulation scheme. So essentially to implement higher modulation scheme I need to have high SNR, right? Because as per your argument I cannot use 16 QAM until I reach this point, because okay, not this point, this point here. Sorry about this. So I should be somewhere around here, because then only my capacity is going to be 4 bps per hertz. So my corresponding SNR should be, let's say, something around 12 dB. So before this point I cannot use 16 QAM, right? So if I have higher SNR, that allow me to use higher modulation scheme, and higher modulation scheme enables us to pack more and more number of bits per symbol. So effectively, let's say like in 5G our common bandwidth is 5G common bandwidth, you will see 100 megahertz. So if I am using 2 bpsk scheme, what is going to be my effective data rate in mbps terms?
200.
uh, no, not
No,
exactly.
sorry. 100 Mbps.
100, because you can only transmit
1 bit.
1 bit per symbol, but I am constrained by my bandwidth because 100 megahertz I cannot really alter. But if I my channel capacity is higher, that is another way of saying my SNR is high, everything is fine, okay, and I decided to use something like 256 QAM, I am allowed to do that, let's say. So in the same bandwidth, what is my effective data rates is going to be here in this case?
800 Mbps.
Yep, it is 8 times, because I can now fit 8 bits per symbol, right? So the choice of modulation scheme is not really up to me. It's highly dependent on your SNR, right? An SNR, so let me write it down here. Choice of modulation scheme depends on SNR, and SNR depend on channel condition. So in a practical system design, it's not really up to me that to choose BPSK, QPSK, or 16 QM or 256 QM or even higher modulation. It's all about, first I need to see what is my channel capacity is, and that I can see in terms of SNR. Only when I know SNR, then only I can decide which modulation scheme I am supposed to use. So now is a good time to ask you, like, then for example you consider downlink communication. So downlink communication is a scenario when basically base station transmit towards the users, right? So my question is, how base station know that what modulation scheme to use for a particular user? Let's say I have one base station here, and I have here user 1, and here I have user 2. Base station wants to serve them both. Now how base station know that which modulation scheme to use for which user? Can one of you answer at this point?
MCS number the user equipment has to send to base station.
Yes. So it's like base station will transmit something like a pilot that is going to received by both users. So users will calculate the SNR, right? And user will just forward the MCS index toward the base station. Then base station know that at which modulation scheme to transmit. So that's okay, that's the modulation part, fine. What about this coding thing? Like, how do you motivate the use of coding here? If I look at the capacity curve, we can say that 4 uh, bps per hertz can be achieved at 12 dB. Similarly 2 bps is achieved at 5 dB. So what about these midpoints? For example, if I would like to choose something like this, let's say what is that, let's say 1.5. So how you can achieve this using only the modulation scheme? Okay, let me write it down here, the question. I'm interested in this part here. So as per our discussion now, let's say I'm operating at this particular SNR. Sorry about this drawing part. So let's say it is somewhere around what is that, 2.5 dB. So in 2.5 dB I find the corresponding capacity as channel capacity as 1.5 bps per hertz. So I want to design my system in a way that it achieves the capacity. So how do you do that? As per our discussion till now, I can use only BPSK, which is capacity achieving for like 0 dB, and or I can use QPSK, which is capacity achieving at 5 dB, but I am operating at 2.5 dB, where the capacity is only 1.5 bps per hertz. So how do I exactly achieve that? Can any of you point it out?
Coding.
Coding. So what is the like concept behind that? I mean, not the maths part, maybe just the intuition part. Like, how do you do that?
Adding redundant
We
bits
can
and putting redundant.
parity bits. Yeah.
Okay, you want to introduce parity bits. Like for example, I guess you are referring to the scenario when you have certain number of message bit and you are going to introduce certain number of parity bits. Depends on your rate. So how does it really work? Like for example, if I consider a scenario like I would like to introduce one parity bit per three message bit. So it's like okay, so it's this is message bit and this is parity bit. So let's say every three message bit I'm introducing a parity bit. So essentially I'm transmitting 4 bits, right? But one of them is redundant. Redundant in the sense it's not carrying any information. So effectively I'm transmitting only 3 bits of information. So what is my capacity here?
3/4.
Well, not exactly. Okay, 3 by 4
Three
in
by
that
four.
case I
Three,
use 2 bpsk, but let's say it's qpsk. Then
three by four into two.
yes. So for let's say qpsk, so it's 1.5 bps per hertz. So even if I am transmitting 4 bits, one of them is redundant. So effectively I am transmitting 3 bits of information, and the capacity or the spectral efficiency comes out to be 1.5 bps per hertz. Uh, Sorry, I don't hear you. Can you repeat once?
I think it was a echo. Nothing else.
Oh, okay, okay, okay. So I am able to achieve this uh, particular capacity, right? And that is achieved via coding. So as you have seen in the lectures, whatever cellular system, even if the most basic one of them, there is nothing uncoded. It's always uh, coded only. Like it's a error correction code, we call it. Just a moment. System getting hanged again and again. Okay. So effectively I am saying I can achieve any point here via use of both adaptive modulation and coding, right? But the question is, if the coding is not there, what are the points we are not able to achieve? I would just like to ask this question before moving on to the next topic.
The in between points like 0 to 1, if the point is in between, then we
Okay,
cannot achieve it.
okay. And what is the loss we are going to suffer there in that case if we are not going to achieve it?
I think the next bit.
No, I'm saying in terms of loss. I'm saying, let's say I'm able to achieve, okay, 1 bits per second, 1 bps per hertz, or 2 or 3, or say, like what loss we are going to see in case we are not able to achieve the intermediate point. I guess my system is not going to be capacity achieving, right? Like for
Yes,
example, if my SNR is 2.5 dB, I cannot go to 2 bps per hertz, because that's the capacity when the SNR is 5 dB and mine is less. So it's not
yes, correct.
exactly capacity achieving. But if I go to 1 bits per second, it's going to be suboptimal for me. Even if my channel capacity is 1.5 bps per hertz, I'm only getting 1 bps per hertz. So adaptive modulation and coding together allow us to design capacity achieving systems. That's the purpose. So with that, let us move to our next question. So if my modulation order is 2 and my target code rate is given, these are the technical forms, I mean target code rate is written in this manner. So what my spectral efficiency is going to be, but before answering that, I'd like to ask what is the modulation order, like in physical terms, what does it exactly mean when I'm saying that?
Modulation QPSK.
True, true. So it's
Number
not
of
on
bits
only
per
for,
symbol.
yeah, it's like QPSK is, when you say QPSK you are being a bit specific, it's about the number of bits per symbol you can transmit. True, exactly. And what does the target code rate in this specific manner, like this shows like 1024 times R is 894, what does it exactly mean?
Number of bits to be transmitted.
Okay, number of bits to be transmitted, but which one? Like there are two numbers, 1024 and 894. So
Out of 1024, we are transmitting 894 bits.
okay, so when we are, I guess you are trying to say that when we are transmitting 1024 bits, actually 894 are the message bits, so those are the useful information. And what are the like what about the rest of them?
Parity bits.
They are parity bits, correct. So how I'm supposed to calculate the spectral efficiency?
So it will be
89.
894 divided by 1024 into 2.
Yes.
Okay, 894 divided by 2 into 1024.
No, no.
Oh, sorry.
894 divided by 1024.
Sorry about that. And what is the answer going to be? Can one of you please calculate?
0.8737.
1.746.
1.7, yeah.
1.74. Okay. So to this extent, if I want to draw the transceiver block, what is it's going to be? For example, let's okay, I start from this part. Let's say this is channel, and this is the input to channel, and this is the output. This is where the noise is getting added. So there are one block here, one block here, another here, another here. So modulation and coding, what should be their order? Should I do modulation first and then do coding?
Coding and then modulus.
Coding and then modulation.
Yes.
So FEC mean forward error correction, that is basically your coder, encoder, and then you use modulator, and then you transmit, and then you demodulate, and then you feed it to the decoder. So what is the purpose of this decoder thing? Can one of you tell me,
Whatever.
Error correction.
okay, and what is exactly the need for it? If let's say I am removing this block from the, like consider hypothetical situation, what will happen in this case?
More bit errors.
We cannot get the message signal.
Basically,
Okay,
FAC tries to
Corrupted bits.
introduce some bits which will help us to actually retrieve the data correctly at the receiver end. If we do not have decoder, then
We cannot get the correct
we will not
information.
get the correct data at the receiver end.
Correct. So there is no way of knowing whether the bits are corrupted or not. Correct. Absolutely. So in 5G NR, uh, 5G new radio, the forward error correction code is known as LDPC code, and this is a capacity achieving code. And one crucial thing to note here that LDPC can, okay, before letting that information know, let me tell you, like for example, consider this scenario. um, let's say my capacity hypothetical for this particular channel realization, let's say my capacity is um 2 bps per hertz, but let's say I decide to transmit uh, at a rate 2.5 bps per hertz. I am not supposed to face any issue, right? Because I am using forward error correction, or I will encounter some issue. What do you think? Because if I am using error correction anyway, the recorder will work, right? Like what is your, like, I would like to know your thought about that. For example, my channel capacity is 2 bps, but I decide to transmit at a rate of 2.5, and my argument is that I am using LDPC coding. So I have this encoder block and decoder block, so it should be able to correct any error, right, or not?
In this case, maybe it can correct
Well, so
because LDPC moves your error curve with few dB. Since you are only zero point 0.5 dB, there is only 0.5 dB difference. LDPC can correct those errors.
Uh, no, that's actually two different points. What you are referring to, I guess that waterfall curve for LDPC. For example, in ideal case, like LDPC, we call it capacity achieving because it can achieve the capacity with a small frequency, sorry, small SNR offset. That scenario you are referring to. For example, for 1 bps per hertz, if the let's say your capacity achieving SNR is 0 dB, LDPC achieve is, let's say, at 0.5 dB. But here we are talking about capacity, not SNR. It's 2.5 bps per hertz. And here comes the critical thing: the no matter how good your error correction code is, it can only correct if you transmit below your channel capacity. If I go beyond my channel capacity, that means I am transmitting more information that I can correct reliably, and that has really nothing to do with LDPC. Like LDPC or any capacity achieving error correction code can correct as long as you are transmitting below your channel capacity. The moment you are going over that, the receiver cannot decode the original message with a arbitrarily low probability. So let me write it down here. LDPC can correct only when transmitter transmit equal or lower than the channel capacity. When this condition is not met, LDPC can no longer save you. So what will save us, that will come next, that's okay. But error correction code has nothing to do with this. The as soon as you go beyond your channel capacity, you are in trouble. Your error correction code is not going to save you. For that you need something else called error detection code. So give me a scenario when it can happen. Like I think in the
Can you
lecture,
increase the modulation?
let's consider a scenario when a user is really close to base station. So it sends the MCS to base station, right? That which modulation scheme you are supposed to use to transmit data to me. So let's say at one instant user is very close to base station, and it tells the base station that okay, you transmit my information with the modulation scheme of 256 QAM. So let me reiterate the scenario. Let's say base station, and this is your user. So user tells the base station that transmit with 256 QAM, that is 8 bits per symbol. And consider a hypothetical scenario. In next few instant this user reaches here, that is very far from base station. So this is near and this is far. So what is the trouble going to happen in this scenario, you think?
Decoding
SNR
errors.
decrease.
And why it will happen? Like what is the issue, like fundamental issue?
Channel changes.
Channel changes, true, correct. And how it's going to impact when your channel changes? What else change?
You'll have high CFO because of Doppler.
Channel changes,
Yeah,
so SNR will reduce.
okay,
SNR will reduce, and then ultimately your MCS will also reduce.
correct, true. But base station already, base station don't have this information yet. I am considering the hypothetical situation when user moves kind of, you say, quite fast. So one of you mentioned Doppler. Doppler is really a complex thing. We are not encountering here it now, at least in this context. We are just purely drilling based on SNR and all that. So the issue, as like you correctly told, that okay, when the user was very close to base station, it asked it to transmit with 256 QAM. Now suddenly it moved to very far. So as you correctly pointed out, again channel changes, your SNR drops. Now your MCS requirement, the MCS index should be much lower, maybe like something QPSK or even BPSK, with which you can decode the message with arbitrarily low probability of error. But the base station don't have this information yet.
Sorry, which information base station doesn't have?
So uh, sorry, can you repeat once? I was not able to hear it.
No, I'm saying which information. Sorry, I could not get which information does base station will not have.
Okay. Base station don't know about this channel change. I mean that information, like user is supposed to report back the MCS, right, to the base station, that okay, my SNR has dropped, so now you please transmit with QPSK or BPSK. So that information hasn't reached base station yet. Base station still transmitting with 256 QAM. So that's the scenario I'm referring to.
Okay, so in that case, I think um, so the if the user is at the far location, then in that case, user will not be able to receive the packets correctly, and then ultimately the acknowledgement will not be sent towards the base station. And in that case, like there will be a HARQ retransmission happening, or I think it will be acknowledgement will not be sent. So I think errors will be quite high in that case.
Okay, true. So let's say base station transmit to with still transmitting with 256 QAM to that user. Now of course the user would not be able to receive the message properly. So this is where your ARQ comes into picture. Basically, uh, the user is supposed to send the acknowledgement back, as you correctly pointed out, that whether the earlier transmission is successful or not, and then only base station usually proceed with the next transmission. So as of now, whatever we are assuming that transmission is being acknowledged even if you don't mention it. So user send a positive acknowledgement that is sent via one message bit, and base station transmit the next block of data. But what if now we are encountering the scenario, what if base station sorry, what if user is not able to decode the message correctly, which will happen in this particular scenario. So user is going to send a negative acknowledgement, right? So
Yeah.
in the course it is this crucial technology, hybrid
ARQ.
ARQ, automatic repeat request, and there are two parts of it. Let's talk about the first one, that is chase combining. So in chase combining, like what happened, like can one of you please tell me, like what does base station transmit? Like it transmit the parity bits or it transmit the message bit? What does it exactly transmit?
It will combine the error bits, and whenever it is able to decode successfully, it will send ACK.
Okay, like yeah, we'll get to there. It's true, absolutely true, that when user able to decode the information, it will send positive acknowledgement. But I am interested in the scenario that what happens in this chase combining protocol. I mean, if this is implemented, like for example, consider this scenario: user move to a far away region, base station transmitted to 56 QAM. The user fails to decode because its SNR now is much lower, so it send the negative acknowledgement. Now at this particular instant, what is base station going to transmit? Is it going to repeat the
Transmit the same packet again.
okay,
Retransmission.
transmit the same
Same data.
packet again? Correct.
Same data. Same data it will
Okay,
transmit.
yeah, exactly. So it will transmit the same data packet again, and this procedure will go on until, of course, there is a limit which, like after which the transmitter will stop. But my question is, how does exactly channel combining work? If I go into the like maths mode, for example, the only issue is
When it
that
is
the SNR
decoding,
is low, right? So how do we encounter that low SNR thing? Okay, let me make
it will
thing.
store the failure packet, and whenever base station is retransmitting, it will combine both the packets and it will transmit.
Okay, so you are saying something like this happen in first transmission. You receive y1 is equal to x plus n1. In second, you are receiving something y2 is equal to x plus n2. Dot dot dot. At mth transmission, you are receiving ym is equal to x plus nm. Right? This is what you are saying is happening. Now base station is going to combine all of them. How exactly it's going to combine?
With
Like
some weights.
uh, sorry, I didn't hear you. Can you please repeat once?
Linear combination, just add them with some weights.
Okay, okay, okay. Let's consider them equal weight. As of now, what will then
Same
happen?
HARQ ID with the different RVs. Based on that, it will combine.
Okay, but how is that combining is going to improve SNR? Because you see that noise is also there, right? N1, N2, and NM. So if I consider any particular transmission, the SNR is going to be P over sigma square. P is the power of X and sigma square is the power of noise. So how does exactly combining is going to help me? Because if I, as you were saying, if I combine them, I mean basically sum them up. So I am calling it Y, which is sum of all of yi, I 1 up to m. So essentially what I am getting, mx plus sum of all the noises, right? So how is this
Forward
going
error
to
means
improve? uh,
FEC.
uh, Not exactly, error correction will not play a role here. We are in the some
We
other
get
domain.
gain from adding all the M transmissions.
We gain from all the m transmissions. Okay, so
Channel capacity will be high.
uh, channel capacity will improve, true, but like it's not channel capacity, like we are working towards improving the SNR, right? Because only when SNR cross a certain threshold, then only I am able to decode what is being transmitted. And currently this P over sigma square is less than that like arbitrary threshold which is required for 256 QAM. So how does this Y help in mitigating that effect? Okay, let's talk about what is the SNR we get from Y. What do you think is SNR going to be?
MP divided by sigma square.
And how does that come? Because SNR expression is
Uh,
power of this and divided by power of this. So what is the
so
power of these terms?
Gaussian MP. If the individual one is P, since we have M transmissions, so it would be MP.
Uh, Not exactly. You are going to have m square p, right?
Oh, yeah, it's amplitude, yes.
Okay,
M
here we
square P.
have m square p. And what about this? Noise usually they are independent because you are
Additive.
receiving at different instant. So the noise are going to be independent, and since they are additive Gaussian, so what is their sum power is going to be? M square sigma square or m sigma square?
M sigma square.
M sigma square, because they are going to add linearly because they are independent. So your SNR is now becoming MP sigma square. So you can see earlier the main reason you are not able to decode because your SNR is less than what is required to achieve the capacity. But now if you keep adding over m such transmissions, your improved SNR is MP over sigma square. So now for a suitable m, there is a good chance you are going to cross this threshold. And that essentially indicates after a certain number of transmissions you will be able to decode what is being transmitted. So that is what chase combining protocol is. I'm sure you know the other one also. What is that uh, name of the protocol? Of hybrid ARQ only, just another variant. So
Incremental
okay,
Incremental redundancy.
incremental
redundancy.
redundancy. So chase combining relies on at its core on multiple transmission and improving the SNR so that eventually it crosses the threshold where it can decode the transmitted message successfully. What is the uh, core idea about this incremental redundancy thing and how it's going to be different from chase combining?
So for
It will
chase
add
combining
each
for
time
every
different parity bits each time. Instead of adding same bits, it will add different CRC bits.
It will add different cyclic redundancy code. Okay, and how is that going to help you?
in chase combining, we are using the same code rate for each retransmission, but in incremental redundancy, the code rate will change.
Okay, so you are saying that at different instant I am going to send different redundancy version. I guess you are
Right.
referring to that, right? So let's say I am picking the example from the lectures only. So let's say user request a 3 by 4 code rate, and you are actually in your transmitter side you have 1 by 4, code rate, but you do puncturing operation. So let's pick this particular scenario where in the first transmission you transmit 3 message bits and 1 parity bits. So you have generated your data as per 1 over phi that contains let's say number of message bit is 3 and number of parity bits is 9, so total is 12. But in the first transmission you are sending this 3 message bit and 1 parity bit, and you want to see whether the user is able to decode it or not. If user has a better SNR, it will be able to decode fine, but what if the user have a lower SNR, it won't be able to decode it. So what I'm supposed to transmit at the next instant?
4 parity bit.
So here it's my first transmission, it fails because the SNR is low, so 1 parity is not going to be sufficient, so I am supposed to transmit another 4 parity bits, and still 5 parity bits may not be sufficient for a proper decoding if the SNR is too low. And what to do in that scenario?
Another set of 4 parity bit.
We will send another 4. So where does it exactly differs compared to chase combining? I mean, what are the aspects that I want to know? First, of course, you pointed out that in chase combining you transmit the same thing again and again. Here it's really depends on certain combinations. Some initially you have to focus more on message bit and less parity bits and want to see whether user is able to decode, and based on that you transmit parity bits. That's okay. So when doing that, what does really change? I mean, okay, let's talk about chase combining. In chase combining, does my effective code rate changes?
No, it will not change
Why will it will not?
because we are retransmitting the same message again and again.
Correct,
The message bit plus parity bit.
correct. And what about this incremental redundancy thing?
Yeah, here only one set of message bit and all are parity.
So
It
what is the
changes. Code rate changes.
so after first transmission, what is my code rate? I mean, for this particular scenario,
It is 3 by 4.
3 by 4 here.
Then 3 by 8.
So when user fails to decode with 3 by 4, it will transmit another 4 parity bit. So no useful information here really. Useful information in the sense no message is being transmitted. So here it's 3 over 8, fine. But it fails now again. So what next?
Then 3 by 12. It's become 1 by 4.
Okay. So next it will be 1 by 4. Fine. So that's okay. There are two variant now, chase combining and incremental redundancy. So which scenario suits what, when to use incremental redundancy and when to use chase combining? Okay, let's pose
So
this let me ask this hypothetical question. Let's see your initial transmission, suppose it's very bad. So what is going to help in this case more, chase combining or incremental redundancy? Like whatever you transmitted in
Chase
the
com
what?
chase combine.
Okay, and why is that? What is the reason behind it?
Think it depends on the SNR.
Okay, it does depend on listener, true. For example, what I say by bad transmission is that you are not able to get almost any message bit at all. So what is the issue there?
Low SNR.
actually in that case, in incremental redundancy, the systematic bit is only first transmission. So you are not able to decode the message bits, then there is no use of this parity bits.
Correct, correct. If the initial transmission is so poor, then the additional parity bits won't help you much. In that case, you better rely on retransmission of the same thing again and again, bring the SNR up to a certain extent, where it can be able to effectively decode. And where is incremental redundancy useful compared to chase combining?
When the initial one is good but not able to decode.
I'm sorry, can you be a little more louder?
When message needs to be transmitted without changing the SNR.
Without changing
When
the
all
SNR.
message bits will be decoded in first transmission, then
Okay,
in that case,
then only parity bits is going to help in next few transmissions. Okay. And which one is the more difficult to implement for a practical system? Chase combining easier or incremental redundancy is easier?
I guess chase combining, because only we have to retransmit the same bits.
Okay. Yes, and incremental redundancy will require kind of a more sophisticated version. You have to first have the design particular code rate, then you do puncturing, then you create different redundancy versions, when to transmit, when not to transmit. And one more thing, like does it really matter, like the order of retransmission, if the redundancy version carry the same information? Like for example, if I, for this particular scenario, let's pick this particular example. This is first transmission, right? This is first, this is second, this is third. Can I just transmit this one, second one first, and then I transmit this one?
In that case, your message bit will be not there in first transmission.
Okay. Yeah, like for example, in certain cases, like for example in LDPC, you put more emphasis on the message bits, which are also termed as systematic bits, as we have pointed out earlier. So they carry more importance. So that's true. Yes, in this case, order matters. But in, for certain codes where the redundancy versions are equal, it doesn't really matter which one you transmit first, which one transmit second. But here it does matter. Okay, with that, I guess this question is pretty easy for you to answer. Incremental redundancy based transmission, your effective code rate is 3 over 4, and receiver failed to decode in first attempt and ask for 2 more retransmission. So what is your code rate is going to be? I guess you just
1
answered
by
that.
4.
1/4.
Yes, correct. And what would be the code rate if it asks for only one retransmission?
3/8.
3/8.
3 by 8. Correct. So this question here talks about bandwidth and subcarrier spacing, FFT and all that. So this is the idea about the OFDM thing, orthogonal frequency division access. So when I say OFDM, so what is the most important thing is about OFDM? What do you think? I would like to hear that. Like what is so good about OFDM?
Downlink.
Ease of implementation.
True.
Multiple carriers. It has multiple carriers.
Multiple carriers. True, true, true. And how
Peak, peak
exactly it's
power
going to
is
help us, like having multiple carriers?
Uh, Channel estimation and equalization is easier in case
All
of
will
multiple
all the
carriers.
carriers will be orthogonal to each other.
Carriers are
Channel
going to be
channel equalize
okay,
channel estimation and equalization is much easier as
much
compared
easier.
to
And how,
more. Yeah.
yeah, and how do you like how you are making it easier? Like it's 50 megahertz bandwidth, right?
Yeah.
It's a
Yes.
very wide band system. So if you go for a single carrier,
Yeah.
there
It
would
is
be
almost flat. It is almost, you can say, piecewise constant, or yeah, or
okay,
the segment wise constant. Yeah.
okay. So what is this idea of segmentation? I mean, are you using a single carrier over the entire bandwidth 50 megahertz, because then the channel is going to be frequency selective, right? I mean, there are lots of ups and downs, and as you pointed out also, your channel estimation equalization are very very difficult. So how do you mitigate that issue?
Using multiple carriers, that's what.
Using multiple
And using,
carriers.
using narrow bandwidth in this 50 megahertz, multiple such carriers.
Okay, so essentially the idea is that you are saying there is this big 50 megahertz thing, and you are breaking down like this, and these carriers you can use to transmit different user signals or multiple signal for one user, right? That's what you are saying.
Yes.
And what does this subcarrier spacing denote?
The distance between two subcarriers.
The distance between two subcarriers. Okay.
Symbol difference.
uh, okay, what do you mean exactly by symbol difference?
Uh, that means the amount of symbol that it can send.
Not exactly. Like when you say subcarrier, they carry different frequency, right? Like
Yeah.
let's say one is centered around baseband, another centered around del F, another two del F, like that. So if I would like to draw the frequency domain representation, something like this is subcarrier 1, this is 2, like that, right? 3, they are all centered around different frequencies. So subcarrier frequency is the uh, gap between them. So I can implement this thing in analog domain also, right? What I am trying to mean is that I have this let's say signals x0, x1 up to let's say xm, and then I do some kind of serial to parallel processing so that I can have all of them in parallel, x0, x1 up to xm, and then what I do, I just modulate over them different subcarriers, as you just say. It's like, let's say 2 pi uh, del f t e to the power 2 pi 2 del f t e to the power j, should be j here, 2 pi m del f t, and then sum them up, and then effectively I transmit it. So what does it mean by multiplying the symbols with e to the power j 2 pi del f t?
FFT.
If I multiply a signal with a exponential in time
You are
domain,
you are shifting your signal to that del F frequency.
okay, so it's like I am loading the symbols onto the subcarriers, right?
Yeah.
And then I'm just summing them up and transmitting. And the subcarriers, as you pointed out, they are kind of orthogonal, so they don't really interfere with each other. And how do I retrieve them? Like for example, if let's say there is no noise, I am just getting in the receiver side xt only. Now xt, what should I do with it?
Say multiply with the conjugate of all the symbols you multiplied with, or all the exponential functions you multiplied.
Okay, so basically you are saying I am supposed to multiply with this and take the integral over one symbol duration for all of them, right? And I am supposed to
Yes.
get back the estimated ones, x naught hat to xm hat. So this can be implemented in analog domain. So this is integrator, and this is the phase shifter and all that. So why don't we implement it in analog domain? Like that looks pretty straightforward to me.
Um, then the components will be RLC, so making your circuit too heavy.
Yeah, the hardware complexity is quite high, even if the maths appears kind of easy. So what is the uh, solution, like way out of that? How do I handle the situation? How do I get rid of this integrator and phase shifter and all that
In digital domain,
in digital
you
domain?
can
That
do.
is much cheaper, much computationally efficient, and all that. Okay. And so in digital domain, what do you exactly do? If I talk about this, we are having the same serial to parallel conversion until this point, I guess. And then what do you do at transmitter side?
Uh,
So okay, in okay, let's try this way. Your symbols are loaded into the subcarriers, right? It's and your subcarriers are frequency, what is that, frequency domain entity. So OFDM is kind of frequency modulation, but what you can transmit only time domain signal, right? So what you need to do in the transmitter side?
you endpoint FFT or
Actually
inverse
FFT,
FFT.
yeah,
Inverse.
FFT, correct. FFT will take you to time to frequency domain. You have to do IFFT or inverse, because that will take you to frequency to time domain. So you will do a endpoint FFT, sorry, endpoint IFFT here. This entire thing will be replaced. Okay, before doing that, what is another essential step that is required for practical implementation? Can you remember something before doing this endpoint FFT, or after that, anything?
Cyclic prefix.
ADC, digital to analog converter you need for transmission.
Okay, that will also come, but yeah, the cyclic prefix insertion is required. So why do we need really that? I mean, why cyclic prefix is required? Can you point it out?
Exactly, we'll get to know where the bits are starting from.
True, but it's kind of a guard thing, right? It protects you against something.
In
ISI.
order to mitigate ISI,
Okay, and why exactly ISI arises? Like in what scenario it can arise?
Multipath. Multipath.
Okay, multipath.
when there is no orthogonality.
Uh, uh, Not exactly. Orthogonal. Okay, can you just clarify the orthogonality part once? What exactly you mean by that? Is that the orthogonality between subcarrier you are referring to?
Yeah.
Okay, that would cause you inter-carrier interference when the subcarriers will
Oh, this is
overlap with each other. But cyclic prefix, as the person pointed out, it is because of multipath, true. But I'd like to understand in a bit more deep manner that how exactly multipath create issue for you. Like, can you go a bit deeper?
So multiple paths, each path arrive at different times.
Okay,
So uh, when you have a second path which is arriving with too much delay,
okay,
so then it interferes with the previous path. So they both combine non-coherently. So your data in each subcarrier is corrupted.
true. So basically, you are saying to protect inter-symbol interference, you are introducing this CP, right? So let's say
Yes.
my cell coverage, that the practical system where I am implementing this OFDM transceiver, the cell coverage is pretty uh, big, I mean in the sense like 2 kilometer or more, do you think I should be more cautious about this intersymbol interference or less cautious? Or
More
I,
cautious. Your delay spread will
More
be more.
cautious.
okay, okay, thank you. So here you have this endpoint IFFT and CP insertion, that's all true. And in the receiver side, what do you need to get back to that original form?
First, you need a digital analog to digital converter, right?
True, you will convert to them to digital domain, fine. Then
50.
Then we
Uh,
will remove the
remove
CP
the
part.
CP.
okay, then you remove the CP.
Then we will take the
Then just
effective inverse of.
True, true. You'll move from time to frequency domain and you will recover your symbols. So if I'd like to answer this particular question, how do I proceed? You have given certain bandwidth, you have certain subcarrier spacing is given, you are given how many points FFT you are doing. So what should be the sampling rate for me?
n times delta F.
N times delta F. Okay, that is a bit about formula, that's correct. But how about a bit, can you just explain me how you are arrived at this particular formula? I mean, for example, when I see the sampling rate, I find a resemblance with the Nyquist rate or something that relates to bandwidth. How is it relatable here? Like if I am given a particular bandwidth, there should be some Nyquist rate, right? If I am
Yeah,
doing analog to
twice the bandwidth.
okay,
You need to sample at twice the bandwidth, right?
okay, twice the positive bandwidth, right? Because when I'm seeing bandwidth here, it's from minus delta F to delta F. So your positive bandwidth is 25, right? 0 to 25, and twice of that is 50, right? Or I'm getting wrong here?
Yes, yes.
No, no, I'm just asking. I'm just okay. So it's my sampling rate is should be more than 50 megahertz. That is confirmed. Okay. So what next? How do I reach there? Like I see subcarrier spacing, but there is also one term called OFDM symbol duration. How is that related to subcarrier spacing?
One divided. It's inverse of subcarrier spacing.
Okay, that is 1 divided by del f, fine. And I also see that in the OFDM symbol duration, you are, if you are doing endpoint FFT, basically you need to take n samples, right? So in a OFDM symbol duration, you are going to take n samples.
Yes.
So if my argument is something like that, if let's say this is t, in duration t, I need n sample. So what should be my sampling rate?
T by n.
Not exactly n by t, just the
No, no.
opposite.
N by T.
Yeah, correct,
Yeah.
correctly. So that gives to what formula you are saying, n delta f, and what is the answer with that?
62. 62 uh, megahertz.
Okay, so exactly I guess it comes out to be 61.4096, I guess something like that. So if you take the ceiling of it, yeah, 62. So with the next thing, the number of slots or subframe, if the system uses a subcarrier spacing of 60 kilohertz. I guess the slot subframe is not covered in the first week's lecture, right?
Yes, it's not covered.
Okay, it's a good point to introduce it. So in 5G NR one
4
time,
slots.
okay, so I would like to start from a bit basics and all that. So when I hear subframe, so there should be something called frame, right? So in 5G NR, what does it mean when I say one frame?
One symbol duration, TU.
No. So let's
A collection of many OFDM symbols.
collection of many OFDM symbols, true, but collections can be really generic. I mean,
Frame.
in 5G specifications, things are strictly like technical, so we have to deal with numbers always. So let's talk about a frame. It's a time domain entity basically.
1 millisecond.
No, 10 milliseconds.
Yeah, so
One frame consists of uh, 10 subframes, and in an hour, the duration is same as of the LT, it's 10 milliseconds.
true, true.
But slot time will be variation of
Depending
subcarrier
upon the
spacing.
subcarrier
So you are saying
spacing.
when
Yeah.
I am talking about subframe, it doesn't really care about the subcarrier spacing and all that. It's always 1 millisecond, right? But
Yes.
when it comes to slot, that is numerology dependent. So based on my subcarrier spacing, it can keep on changing. Is that what you are referring to?
Yes.
Okay, okay. So fine, one frame has 10 subframe, okay. And then how many slots per subframe?
Depends on the subcarrier spacing. In this case, 4.
Okay. So let's start with the 4G LTE one. There is only one subcarrier spacing allowed there. That is del F is 15 kilohertz. So for this particular subcarrier spacing, what is the slot duration?
1 millisecond.
So basically you are saying that subframe and slot overlap there. Like overlap in the
Each
sense
subframe contains only
each
one
subframe
slot.
contains one slot, correct. So if I move to 60, there should be
4 slot within the subframe.
four slots. And what is so important about one particular slot? Like what I'm asking, what is the significance of one slot? Okay, let me give you kind of a hint here. Uh, you already know that user like in a
The
cellular system. Yeah, you are saying something.
So it will search for every delta, like whenever the subcarrier spacing are increases, because in NR we have large bandwidth, right? So if you are using less subcarrier spacing, so it will take more time to find out the cell or something.
Okay, in 5G you are actually use dynamic subcarrier spacing, true, but in 5G you are also looking at two bands. First one is called FR1, which I am sure you have gone through. This is also called sub 6 gigahertz band. That is anything below sub 6 gigahertz. That is FR1, and here your maximum bandwidth that is allowed to you is 100 megahertz. And the second one it uses is FR2. It is also referred to millimeter wave band, and here the it's between 24 point, I don't exactly remember the number, 24 point something to 52 point something gigahertz, where you are allowed a maximum bandwidth of 400 megahertz. So if I let's uh, let's get a bit deviated. If I ask you to design a cellular system where I want to cover a lot of area served by one single base station, which frequency band you are going to choose?
Up 6.
Sub 6. And why is that so?
Coverage.
Because
Coverage. So you are saying that if you have a lower frequency, your propagation loss is going to be less, so you can cover more distance. Is that what you are referring to?
Yes.
Okay. So for FR2, your coverage area should be lower. So what is the impact of subcarrier spacing on the CP duration? I guess that one is covered probably in the last lecture. But I'm asking that if your subcarrier spacing increases or decreases, does it impact your CP duration or it really doesn't?
Yes, it will impact. It will impact.
It will impact. In what way?
When subcarrier spacing increases, then CP duration will be decrease.
Subcarrier spacing increase, then CP duration will be decrease. Okay. So FR1 or FR2, which one is more likely to have a higher subcarrier spacing? Okay.
FR2.
FR2 is have more subcarrier spacing.
Okay. And is that going to help it in terms of mitigating the intersymbol interference? I mean, in terms of CP duration, like does they both align or they have uh, different requirement? Like if you have a higher spacing, your CP duration also reduces, right? So for FR2,
Yes.
it's beneficial or it's creating problem for it?
it's beneficial. Increase in spectral efficiency, right?
Not exactly. Okay, what I'm trying to ask is, for example, you mentioned that subcarrier spacing is more in case of FR2, but also you pointed out earlier that more subcarrier spacing mean your CP duration decreases. So will not that create a issue in terms of mitigating intersymbol interference?
Yes, but also delay spread will be less when you go to higher frequencies. So even with shorter CP, you can live with it, right?
Yeah, so they kind of align. That's what you are pointing out, right?
Yes.
Good. Okay, let's come back to this slot thing here. So yeah, as why I was asking, what is the like significance of one particular slot, like how many symbols it contains maybe or something like that. I think one of you
14
already
symbols.
mentioned they have 14 symbols, right?
Yes.
And you also know that base station makes all the decisions, right? Which user to serve, where to serve. So this scheduling decision, how frequently they happen, you think? Does it happen every frame, every subframe, every OFDM symbol, or every slot? Like usually.
Maybe every slot.
Yeah. So every slot users usually make a decision. So in every slot you have 14 symbol, and okay, this is a good point to introduce that in OFDM basically we are mapping symbols in a time frequency grid here. So if we talk about this is frequency. and this is time. So here you have first symbol, second symbol, third symbol, like that, and here you have first, second, third subcarrier, like that. So how many subcarrier you usually have? Let's say if you have this
12.
50 megahertz bandwidth and you have a subcarrier spacing of 15 kilohertz, then roughly what is the number of subcarrier you have usually?
12.
3300.
Yeah, so it's 50 divided by 15 times 10 to the power minus 3, so that's essentially 330. Actually there is a guard band of zero point 0.5 or 1 megahertz, so essentially it reduces to 3300. So is it possible for user to schedule uh, sorry, is it possible for base station to schedule a user on one subcarrier only and the next subcarrier is on to some other user? Like, can you do it on a per subcarrier basis?
No.
So how is it being done?
Group of subcarriers.
Group of
And is
subcarriers.
there any limit of this number of subcarriers in a group? Maybe like some higher limit,
Twelve,
or
I
what?
guess.
12. Okay, 12 is the minimum limit. So if you have to assign user, you have to minimum assign 12 subcarriers, and
Into
uh,
14 symbols.
and in multiple of 12s of that, right?
Yes.
Okay, so what does that call, like this group of subcarriers?
Slot.
PRB.
PRB, right? Physical resource block.
Physical resource blocks. Yeah.
So in one slot you are basically having 14 OFDM symbols. If you look at in the time domain, if you look in the frequency domain, you have 3300 subcarriers, or if you want to talk about PRBs, it's the whole thing divided by 12, that is 275 PRBs. In one slot, this many samples you have in your hand, and you can schedule the user based on that. So it's a good time, I guess, to how many users you can schedule, maximum number of user in one slot. Can you tell me the number? If a slot has 14 symbols and 275 PRBs, how many user you can schedule here maximum?
275.
275, true. 275 is the number of PRBs, that's okay, but you have also 14 symbols, right? There is no necessity that you have to assign every symbol to every user.
It should be 275 into 14.
Yep, 275 into 14. That comes out to be what, roughly uh, more close to 4000, right? But that's the theoretical thing. In most practical system you will see not more than 40 to 50 users being scheduled at max. Okay, so for this one the answer is 4, as you mentioned. And what is the each
So
slot?
one. Can you repeat again? One slot has got how many
Okay, one slot you have 14 OFDM
symbols?
symbols, and you have
Okay.
275 PRBs. So you can assign one user, you need to assign minimum one block, and you are going to assign minimum one symbol. So if there are 275 PRBs and 14 symbols, then maximum number of users in theory you can accommodate is 275 times 14. That is I guess close to 4000 somewhat, but in practice it's orders of magnitude less. Like 40 50 max, I guess, get scheduled by the base station per slot.
So why only
Okay.
14 symbols?
uh, Sorry, I cannot hear you, can you repeat once?
Why only 14 symbols are in a slot?
Okay, that's what it can contain, right? Because your slot duration, what does it depend on? Like you are asking why there is only 14 symbols in a slot, right?
Yes.
Okay. So that's a standard thing. So I mean, you are asking why the 14 number coming or something?
Yeah, only 14 number coming.
Okay, okay, okay. That is as per standard design. I don't really know like behind like choosing the the reason behind choosing this particular number. It's just standard. I mean, there is of course possible some reason behind it, but like I don't really know it.
And what is the subframe?
uh, Subframe is like each frame contains one like 10 subframe, and each subframe
Sir,
is of
please explain this frame concept. Frame.
yeah.
So what is subframe?
Okay, 10
What is the
subframe.
subframe?
Hello, you can hear me, right?
What is the subframe? What is the subframe?
Okay, your 10 subframe consists of one frame, and each subframe is of 1 millisecond duration.
Okay.
So that's its significance. It's a numerology independent term.
No, that's fine. That's fine. That's fine.
Okay.
Only
So
subframe is important, or frame concept is there in 5G NR?
important in the sense, well, to best of my knowledge, um, like I haven't dig much deeper into that. I just gone through the lectures. So in terms of important, I don't really know about that, but it's about that hierarchy that's I find kind of important. That one frame consisting of 10 subframe, and subframe being is a entity of that is of 1 millisecond duration, irrespective of your subcarrier spacing. But then comes your the slots, which are subcarrier dependent. So based on your subcarrier spacing, your subframe can contain single to multiple slots, and slots being entity where uh, that decide the frequency of scheduling the users. And each slot of course contain these 14 symbols and 275 PRVs where you can accommodate the user. So that's what I really know until now.
Sir, this is same for FR2 also.
Yes, yes, it's same for FR2. It's just when you go for a higher and higher subcarrier spacing, you will have more and more number of slots per subframe. But the subframe is always of 1 millisecond duration.
It is all as per 3GPP.
Yes. So they have all these numbers and standards in the place just to be what is that for convenience of system design. That's all.
Okay, sir. Thank you.
Sure. So we'll answer this question for me. We'll have the bandwidth and subcarrier spacing as in the previous question. So is the number of samples, FFT samples. So what is the CP length of the first symbol if rests of the symbols have a CP length of 288 samples? So how I am supposed to answer that? Like any idea which direction I should move or something?
So number of remaining symbols divided by the total number of CP.
Uh, divide the symbols by total number of CP. Can we start from like how many samples are there per symbol?
4096.
4096. And
Should be there.
sorry, I cannot hear you. Can you just repeat once? Okay, so just a minute. So how many so this is 15 kilohertz of subcarrier spacing, right? So one slot duration is 1 millisecond. So how many samples we are going to have in 1 millisecond?
One subframe in 1 millisecond, no? One
Yes,
slot
yes.
is 14
14
seconds.
to
It's since it's 15 kilohertz, our one subframe and one slot, both duration are 1 millisecond, right? Or I'm getting it. Uh, yeah, I guess for 15 kilohertz, our subframe is also uh, 1 millisecond. Can one of you please confirm it?
yes, yes.
Okay, thanks. So let us calculate the number of samples per slot. So in each slot I have 14 symbols, and each symbol, how many symbols do I have?
4096 into 14. I have one question.
Yeah,
Oh, divided by
Uh,
14.
yeah, you have question.
uh,
Yeah.
why, why are you calculating per slot? Because they only asked for one OFDM symbol, right?
Yes,
Because he
So,
considered that the subcarrier spacing as 15 kilohertz. So in that case, subframe contains only one slot. So that's why he's calculating for slot.
I guess that's clear to you, right? Or
no, it's not. Can you please?
okay, okay. So what I am saying, like for when you have 15 kilohertz subcarrier spacing, your subframe is also 1 millisecond duration, and your slot is also for 1 millisecond duration. So here I am supposed to calculate the CP length of fast symbols if rest of the symbol has a CP length of 288 samples. So just a moment. So the reason is that when you have a particular sampling rate, and that is not exactly going to match when you add this number of samples and CP times symbols. So there will be some extra symbols that don't really carry any information. It's just to fill up the gap. I think that will get clear once we'll get to the answer.
Okay.
Actually, that question mentioned that in the slot you have 14 in the slot you have 14 symbols, and all of them supposed to have 288 samples, but you will see there will be some extra number of samples which are basically added as a CP on top of the first symbol. So that
Okay.
is the kind of like the reason. So okay, let us first find the number of samples per millisecond. So what is the sampling rate for this system? We have found it earlier, if you remember.
61.44
Yep,
megahertz.
61.44 megahertz. Sampling rate is 61.44 megahertz. So if one slot duration is 1 millisecond, how many samples per slot? 61.44 into 10 to the power 6
61.44.
divided by 10 to the power minus 3, right? That is 61.440 number of samples I will have in one slot. Now how many samples per OFDM symbols? Samples
4096.
per OFDM symbol 4096. What is the CP length per symbol?
288.
288. So effectively, how many symbols? How many samples I am having per symbol? 4, 3, 8, 4. Right.
Yes.
So and how many symbols I have? 14 symbols.
Hmm.
14 symbols. So what should be the effective number of samples?
14
Like
into
not redundant ones. Yeah,
438.
14 into 4, 3, 8, 4. And let me calculate that once. 4, 3,
It
8.
would be 64 less than 384 into 14. It would be 61376.
61376. So that is what is necessary for you. If you have a CP length of 288 and number of samples, of course it's already fixed by the point 50 points, but your sampling rate is 61.44, you already found, right? So your samples per slot is 61440. So what is the difference between that?
64.
There is 24 here and the 64. So 64, and these are kind of redundant, right? I mean they are acting
Hmm.
as a filling. It's just between the discrepancy between the samples per slot you are supposed to have versus the important information. Im- okay, when I say important information, I mean both the message samples and the CP length, both are important. And there are 61376 uh, necessary information per slot, and according to sampling rate there are 61440 samples. So there are 64 redundant thing samples you should fill, right? So I guess this answered your question, that why exactly I was looking for one slot instead of one symbol.
Yes, it's clear now.
Right. So according to the sampling rate, I am supposed to have 61440 samples, but I have only 6161376 important samples, and the 64 will be redundant. And this what we usually do, this we add to the CP length of first symbol. So remember the first, all the symbols already have 288, right? On the first symbol we add this 64. Basically 64 is the additional CP length. So for first symbol, the effective CP length for first symbol, effective CP length is 352.
352.
Yeah,
352.
that means basically you are picking the
So,
last 352 of this 4096 samples of first symbol and putting them as the CP. That's all. So this
okay.
is what
I
is
have a
happening.
question.
Yeah.
So, whenever UE receives OFDM symbol,
Okay.
will this information be is added to some header, or it just keeps track if it is first symbol, and then it will remove 352 instead of 288 samples? Because if it removes wrong number, then synchronization would be lost,
Of
right?
course, the message information will be lost. True.
Yeah. So how does UE know whether it is the first symbol which it received, or yeah, yeah,
Okay.
or this information is already hidden in header?
As per my understanding, as of now, the base station instruct the user, right? I mean, in this time frequency grid, I mean like which symbol and which subcarrier it should look into for its information. And as you are mentioning that the extra CP length, this information should also be included, otherwise it is not of course possible for user to know that that redundancy is being included. But if you ask
Okay.
about the exact location, I don't really know now, but yes, this information need to be conveyed beforehand, otherwise user will be in trouble.
Okay. Okay. Thanks.
Yep. So we have this last question, and since we have discussed is pretty well, so what should be the answer here? The slot duration and subframe duration, the product of it. The only thing changes here is the subcarrier spacing, that's all. So what do you think is going to be the answer here? Anyway, your subframe duration is always constant no matter what. And what is going to be a slot duration here?
0.5.
Correct. So effectively it's only 0.5. So the fourth one is the correct option. So with that, the number of questions I wanted to discuss kind of ended. So if you have any kind of questions from your end, you can just ask me. Please don't hesitate. I'll try to answer
Will you
my
share
best.
these questions with us?
Yes, yes, sure. I'll upload this, and the upload link and this video link also will be shared with you. Uh, Actually, that notification will come into that course web page. It usually come within first week only. I mean it's not now there probably, but I, from my experience, within 3-4 days they will like upload it. And of course I will upload
Okay.
this presentation also, and the video recording of this session will also be available. So and any more questions or anything in general about this course?
In one of the assignments, one of the questions in the assignments,
Okay.
like incremental redundancy, do you need to know basic rate? Only effective rate is given, like 1/4. Do you need to know basic rate?
Okay, what they refer to basic rate here? I mean,
It's not given, not given in the question.
okay. Uh,
I'll
no.
copy paste the question. I'll copy paste the question in the chat.
Okay, okay. Just let me take a look at it. The 5G system
Underline.
which uses incremental redundancy retransmission mode with an effective code rate 1/4 data initial transmission successfully decode the data in the first attempt and requested for to calculate the code rate at which receiver was able to successfully decode the data. Uh, no, I think base rate is not required here.
Okay. So effective rate is given 1/4.
Yes. The effective rate is given at the transmitter end. So
In the
usually,
initial transmission. In the initial transmission, the first one. original transmission itself is 1 by 4.
Uh, Sorry, can you repeat once?
In the original transmission itself, the effective rate is 1 by 4.
Yes, like at the transmitter end.
Yeah.
Transmitter,
Yeah.
the effective code rate 1 by 4, but of course in the initial transmission it is not
Receiver
going to
failed to decode it. So two more retransmissions were requested by the UE or the receiver. So I mean, the basic rate is not given. So how do we take into account how many in subsequent retransmissions, how many parity bits are sent? How to find out that?
okay. I guess,
And
yeah.
that will give us, I mean, effective rate. That will let us know, I mean, let us calculate effective rate. So how many bits are to be added? 3 bits or 4 bits?
Okay, yeah.
1 by 4 means there are 3 redundant bits in the first transmission. So do we need to add three more or what?
Okay, yeah, I think that clarity is somewhat is not there. Most
I
likely
think initial transmission can be taken as 4 bits.
Initial transmission is 1 by 4. Effective rate is 1 by 4.
Yeah,
So
so initial
one
transmission we can
message
take
bit,
it
three
as
redundant
4
bits.
bits.
One message bit, 3 redundant bits. It has
Yeah,
transmitted.
like that we can take, I think.
And then in the second retransmission, in the first retransmission, how many redundant bits? 4 or 3?
In first transmission, it will be 3 by 4 plus 4.
Why 3? It is 1 by 4. No, in the initial effective rate in the first transmission is 1 by 4.
No,
Not 3 by.
it will be 1 by 4
It's
plus
not
4 only.
basic rate. It's effective rate. It's not
Yeah, we
basic
can.
rate.
I think we have to take it as the mother rate.
So what is the rate that we need to consider? Basic
1 by
rate.
4 only.
Why 1 by 4?
Because it is initially given as the
Basic rate
1 by
can be
4.
anything, no? Basic rate can be 1 by 4 or less.
Yeah, it can be 1 by
Because
4 or less,
incremental
but
redundancy might use
for
puncturing, right?
proceeding the question, we can take it as the mother rate only, 1 by 4.
So what is to be taken? Yeah, basic rate. Because incremental redundancy, I mean, believes in puncturing, right? So we require additional bits in the basic rate so that puncturing can happen.
Yes. So in next
So
retransmission,
if the basic rate is same as initial rate, there is no puncturing.
yeah, in the retransmission only puncturing happens now, not in the initially.
Initially also puncturing happens, right?
No, in IR, I
Right in
think
the
it is
beginning,
only
like think of,
in
I
the
mean, 1 by
if
4.
retransmission is there only, puncturing is there.
Think of 1 by 4 basic rate and 3 by 4 effective rate in the beginning. The transmitter is going to, I mean, generate 3 message bit 12 bits, and it is going to send 3 by 4. So puncturing happens there. It will discard what?
Yeah, as per my
8
understanding in
bits.
the
Yeah,
lecture, it
8
is told
bits.
that if there is retransmission, puncturing is there in IR for every retransmission.
Even the first one also puncturing happens. No,
Yeah,
all the
first
redundant bits are
retransmission
not sent.
only. Yeah,
In
first
the first
retransmission
original
only.
transmission, 3 message bits and only one of the redundant bits are sent, not all. So effectively puncturing happens, right?
Don't know. I think it is only in retransmission only.
Yes.
Yeah,
Yeah,
I think
your views.
I also think this is a clarity would have been nice. Like more clarity would be required. It can be interpreted
Yeah,
in two different ways, like as you said. True.
correct. So in retransmission, how many bits are to be considered so that we can find out effective rate in the first retransmission, then second retransmission, and then we can compute effective rate. So that information is somehow not there in the question.
But when you say that number of bit to be the retransmitted, it remains same, right? For example, if I transmit with the code rate of 1 by 4, in the first transmission, let's say you are transmitting one message bit and three parity bit, and the
Correct.
receiver fails. Of course, it
Yeah.
next adds another four parity bits. It's going to transmit, right? If I assume that all the systematic bits are transmitted in the first transmission,
Okay.
then it will
So
become
Only one message bit, right? So one message bit, one is transmitted, three parity bits.
Three
So the
parity
next
bits.
retransmission, it is going to transmit 3 or 4 bits.
Four. The number of
Because
bits.
there are three parity bits. There are
Next
three
also, I
parity
think
bits.
4 bits will be transmitted. 4.
There are three parity bits. So maybe in the second, version,
Yeah,
it will
1 plus
transmit,
3, 4 bits will be transmitted in the next retransmission.
and in the second one also 4.
So
Second one
effectively,
also again 4.
so it would be
So it is 3
effectively.
by 12. Then 3 by 12. So 1 by 4 once again, same. So it is same as that of chase combining.
Uh,
It is saying the incremental redundancy is same as that of chase combining.
um,
If message as well as parity bits all are sent, it is same as that of chase combining.
yeah, true. But this term here, this effective code rate, I find it a bit of integrating, because if we consider like compare with the example in the lecture, where it's like the even if the user asks for 3 by 4, the transmitter actually do 1 by 4, and in the first transmission it transmit an effective code rate of 3 by 4, because it has those
Correct.
like for 3 message bit and 9 parity bits, it ignored the 8
Correct.
parity bits and send only one, and checks
So
whether
that is effective. That is puncturing, right? That is puncturing.
yes, that is puncturing.
Yes. So even in the original transmission, puncturing happens.
So here I am thinking, can it be possible that by effective code rate here they are meaning what is the code rate in the first transmission? Maybe, but the actual code rate is much lesser. But for first transmission, is the code rate is 1 by 4? Is it like that? I'm also
So
a bit
that is
confused here.
unless basic rate is given, no, we don't know how many things are to be considered, and then
And what are the options given there?
I'll copy paste options.
Okay. Okay. 1 by 4.
ChatGPT says 3 by 7. But it doesn't tell how to compute, right?
Okay, my guess is 1 by 12, but I'm not really sure about that.
So it's not about asking, what the questions in the assignment, because things are not much clear in the question that I asked.
That clarity is somewhat is bit missing
Hmm.
there.
And then TAs are not responding there. TAs of the
Okay, I will try contacting
yes,
them, and if
yeah,
I get to know something, I will answer. Like
yeah.
you are
Please,
referring
please
to
post
that
on the
group, right? That Google
assignment
group.
question, assignment question number 6. It is
Assignment question number 6. Okay, okay.
assignment number 1, assignment number only one assignment. So question number 6.
Okay, so I will ask
So
the
clarity is required. We don't want answer. Clarity is required.
Of course, of course. I get that.
How to, how to, we know how to compute,
Uh,
but how many bits are to be added, we don't know.
yes, yes.
So it is a wild guess only.
I get it. I'll contact them, and if I get the clarification, I will like
Yes,
update the
please post
same
it
in the
on QA
group.
group.
Sure, sure.
Uh, there is a QA group and there is a QA, right?
Yes,
Question
yes,
answer.
yes. Sure.
So please
Question number.
update there. Yes, please.
Okay, okay.
Yeah. Thanks. Thanks.
Sure.
Okay. Bye.
Bye, bye. So if any of you have any more questions, then I will take it. Otherwise, we can conclude the session for this week. Okay. Thanks everyone for joining. We'll meet next Saturday again for the discussion regarding assignment 2. Bye.